Use freefall kinematics and Newton's first law to answer each of the following questions. In part A, you get a 1 kilogram rock that's dropped from rest from a height of 80 meters, and air resistance is negligible. We want to calculate the speed of the rock after 2 seconds, so we're just going to use some freefall kinematics. And with kinematics, you don't need to know about the mass, so let's just write down the stuff we know. The initial velocity is 0 because it was dropped from rest. If we define downward to be the positive direction, since the rock is only moving downward, there's no upward motion, we can then say that A is equal to 10 meters per second squared, the acceleration of gravity. And we want to know what is the speed after a time of 2 seconds, and we're looking for the V. So use the appropriate kinematics equation to get the answer of 20 meters per second. And that's a pretty basic one, so I'll let you show the work on that one. Alright, part 2, calculate the height of the rock above ground level after 2 seconds. So let's just continue with what we were solving, and instead of looking for the V now, we are looking for the delta Y. So pick the appropriate kinematics equation that has VO, A, T, and delta Y, and if everything is done right, you should get a delta Y of 20 meters. Now keep in mind, that's how far the rock has fallen. But the question is not asking for how far the rock has fallen, it wants to know the height of the rock above ground level. So if we have this rock that was dropped from a height, the total height was 80 meters, the 20 meters is just how far the rock has fallen up to about this point right here, which means the height above the ground, just subtract them, and you'll get the height as 60 meters. And for part 3, calculate the speed of the rock just as it hits the ground. So let's look at which variables in our list we can use and which ones we have to get rid of. The initial velocity is still 0. The acceleration is still 10. We can no longer use this t equals 2 seconds because t equals 2 seconds, the rock had not yet hit the ground. So we'll X that one off the list. And when the rock hits the ground, we now know what the delta Y right here is equal to. It's not 20 meters. When it hits the ground, it has fallen a total of 80 meters. So we'll X this one off the list and replace that with a delta Y is equal to 80 meters. Since we defined downward as the positive direction right here, this can be a positive number going downward. If we had defined downward as a negative direction, then both this and this would be negative. Okay, and we're trying to find the speed of the rock when it hits the ground. So the V is what we're looking for in this case. So you want to pick the appropriate kinematics equation that has VO, A, delta Y, and V in it, and is missing the T, and that will give you a final speed when hitting the ground of 40 meters per second. Now in part B, we have the same rock, 1 kilogram, is dropped from the same height, 80 meters, but this time the air resistance is no longer negligible, so it's going to factor into slowing down the rock because of the drag force, and it tells you the drag constant for the rock in air is 0.4 kilograms per second. So this problem is a little bit easier to see if we draw a free body diagram for the rock as it's falling. So on this free body diagram, we're going to have a downward gravitational force and an upward drag force. And when the rock has reached terminal velocity, which is what you're asked to calculate in part 1, the drag force will be the same as the gravitational force. So we can say drag force equals gravitational force. That's just Newton's first law. The drag force equation was BV. That's equal to mg. And we can solve this for v just by dividing both sides by b. M times g, that's going to be 1 times 10, so 10 in the numerator, and the b is given as 0.4, so 10 divided by 0.4 gives you a terminal velocity of 25 meters per second. And then in part 2, determine the speed of the rock just as it hits the ground. Well, if this is the terminal velocity of the rock, and it reached that terminal velocity when it's halfway to the ground, it's just going to keep falling at that same speed. So when it hits the ground, it's going to have a speed of 25 meters per second, the same terminal velocity.